Our first talk is by Paul Hain on analysis of thermal data from LRO Diviner and thermal eclipses.
Okay, good morning. Thank you very much. So, like a few other people, the title that I was assigned was not one that I submitted, so my actual talk will be a little different. But I just wanted to pick up an animation of a model that we developed on the Diviner team that's based on David Page's 3D thermal model for the moon. And so what you're seeing here is the south polar temperature evolution over, I believe the whole animation is 1 Earth year. And I just put this up to emphasize the complex and kind of strange nature of temperature and infrared remote sensing. So if you look at this scene, obviously we've got a huge range of different temperatures. The scale bar here goes from, sorry about that. The scale bar goes from 40 Kelvin up to 400 Kelvin. And even at these high latitudes, the illuminated surfaces experience temperatures that go all the way up to 400 Kelvin with the peak temperature at the equator as well. So I'm going to talk about the moon's thermal behavior, but I want to, as much as I can, try to relate this to some of the earlier discussions and talks that we've had here. I know I've learned a lot so far this week, coming at this from more of a planetary science geophysics perspective rather than astronomy. So in addition to my authors here, I wanted to just put this acknowledgement up because unfortunately I don't have time to go over the full history of lunar infrared remote sensing. And there's this long and illustrious history going all the way back to the 19-teens or even before, when people first started trying to measure the temperature of the moon. And a lot of these papers from the Apollo era, the 1960s through the 80s, really kind of form the basis for the science I'm going to talk about. And so these are some of the names that come up over and over again. Like I said, I don't have time to go into their work. I'm just going to focus on the work that we've done with all due respect and acknowledgement for everything they've done. Okay, so this is what the moon's equatorial temperatures look. So here we've got the nighttime temperatures down around 100 Kelvin or down to 90 Kelvin by just before sunrise. The red line is a model, and the gray points are Diviner data. I'll tell you what Diviner is in a second. But what I wanted to point out here is just that what you're seeing here in the data is not noise. Every single one of these points is telling you something about the thermophysical or thermal behavior of the lunar surface. And what I'm going to do in this talk is basically go through each different part of this thermal curve and talk about what those different parts of the curve are telling us. So those things are, so using these radiometric measurements of the lunar thermal emission, and this is true for any airless body, with multiple spectral channels, measure that thermal emission, we can get constraints on the temperature distribution within our measurement field of view, the rock or block abundance on the surface, the regolith structure, so that's typically quantified by the thermal inertia or the porosity. In our case, we get a depth profile of that. The surface roughness is a huge effect on airless bodies. And then so this has implications for volatile stability, which is a whole different talk, and I don't have time to talk about that too much, but Lior is going to talk about that after Rebecca Gent's talk, in 3 talks. And then from thermal infrared measurements, we also get constraints on composition, which again I don't have to talk about, but the Oxford group will talk about that in more detail this morning. Okay, so just to kind of whet your appetite, this is some Diviner data from very early on in the moon. Looking down again on the South Pole. So this is 2 different spectral bands, and what you notice right away is that there's obviously similarities in what you can see in both the different spectral channels, at shorter wavelengths, you're kind of missing a lot of the colder regions. And when you go out to longer wavelengths, those pop out. And so I'm putting this up here because one question you could ask is, if you, instead of getting this kind of mapping capability, you just assume that each one of these is one of your pixels, or if you have a full disk observation, for example, that contains this kind of temperature distribution, if you're measuring it at 8 microns, you're getting a very different signal than you'll get at 50 to 100 microns. And so that's an important fact that plays into all the techniques that we use to test the thermophysical properties of the lunar surface. Oh, and just for reference, the coldest temperatures that we're measuring here up in this region, and there's one more down here, that are at most 25 Kelvin. So these are some of the coldest surfaces in the solar system. This is a little bit of review. I think everyone knows this, but I just want to provide a little background. So the depth of penetration of a thermal wave depends on frequency of the wave. So if you have, and this is just an idealized sinusoidal temperature forcing at the surface, and that propagates downward with a depth that's dependent on both the thermophysical properties of the material, but also the frequency of that wave. So the lower the frequency, or the longer the period of the wave. So this is a 29-day period, which is the lunar synodic period. Compare that to a period of a few hours, which could correspond to a rotation period of an asteroid, or a lunar eclipse. So in the case of 29 days, you penetrate down to a depth of a few tens of centimeters, whereas the few hour eclipse penetrates to a depth of about a centimeter. And so we can use thermal waves of different frequencies to sense different depths within the surface. And the important fact for studying small bodies here, I think, is that it's important to keep in mind that when someone reports a thermal inertia value based on thermal infrared measurements, really only telling you the thermal inertia over this depth that they're sensing. And in fact, it's sort of a weighted function of the contributions of these different depths to that measurement. So you have to be a little bit careful about quoting one thermal inertia value for an entire body. Not only does it vary over the surface, but it also varies with depth. And I'm going to show you evidence for that from the moon. So here's how this works, kind of, so the lunar diurnal curve has this massive amplitude, and that's primarily due to the slow rotation. It's got a 29-day rotation period, effectively. So during the day, even though temperatures rise all the way up to effectively radiative equilibrium of 390 some Kelvin, at night, because the regolith is so insulating, it drops down to less than 100 K. Here's another example from a fast rotating near-Earth asteroid, where you get roughly the same mean temperature, but it's much more constant over time. This is just a curve series, just for example. Okay, so Diviner is an instrument on reconnaissance orbiter. We've been in orbit around the moon since 2009. We're still there, taking data right now. It's a push broom mapping radiometer. We have multiple spectral bands spanning from the visible out to the mid to far infrared. Our longest wavelength channel goes about 100 microns out to 400 microns wavelength. And we have some compositional channels at 8 microns, and then a few more in between. So we can measure temperatures all the way from the coldest 25 Kelvin surfaces at the polar regions in permanent shadows, all the way up to the peak daytime temperatures, or even higher if we wanted to. So we've got 21 pixels across track, and we sweep out. This is obviously not to scale. The total array across here is typically a few kilometers, and each measurement has a spatial resolution on the surface of a few hundred meters. And we've gotten complete global coverage. These are early maps, so you can see some data gores and things, but we've basically been mapping since 2009. We've filled in the entire moon's surface at this 100-meter resolution at essentially every local time at every point. So if you give me any point on the moon, I can give you the entire diurnal curve, more or less, of that particular point. So it's a very unique data set. Our coverage, because we're polar orbit, our coverage is actually much better at the poles. So we get many, many observations over 1 year cycle at any location at the poles. And so these are some early results looking at the distribution of polar cold traps where water ice could be trapped. It turns out there's thousands of, hundreds of thousands of square kilometers of real estate to trap water ice at the lunar poles. Okay, so getting back to the diurnal curve, these different parts tell us different things about the thermophysical properties of the surface. So these spikes you see here, and this is for one particular location, so this kind of beating that you see is not real. It's an artifact of the particular local times that we have coverage for. But the spikes and their distance off of this model curve are real, and this is showing you warm rocks at night. So the nighttime regolith temperatures, again, drop down below 100 Kelvin. Rocks remain warm due to their high thermal inertia. So we can use these data points to constrain the surface rock abundance. So this is shown here. You can model what temperatures you expect for rocks of different thermal inertias, and you can pull out from that multispectral thermal signature what the contribution of these different components is. And that's what we've done. So this is work that was first published in 2011. We're still refining the technique and looking at the rock size distribution, but this is the basic idea. So if you have say this is your pixel on the surface and you've got a rock in the middle, this is nighttime temperature. The regolith is very cold, the rock is warm. And what that does is, so size here, but the bottom axis is wave number or wavelength on top. So longer wavelengths are to the left and shorter wavelengths to the right. So the shorter wavelengths, as you increase the rock abundance, so this temperature down here is the regolith temperature, 90-some Kelvin. You start adding rocks, so here's 2% rocks, 5%, 25, 50%, and then 100% rocks. In this case, we modeled the rock as having a midnight temperature of 185 Kelvin. What you see is that not only do all the brightness temperatures go up, so this is brightness temperature. So this is essentially what you're measuring. And I should mention that with a thermopile-based radiometer instrument like Diviner, we're actually directly measuring the brightness temperature, not radiance. There's no calibration systematic errors or anything like that. So we're directly measuring points on these curves. Excuse me. And so if you look at the different Diviner channels that we use for the technique, here's channel 6, channel 8. We get a spectral slope in the brightness temperatures that we measure. And because that slope depends on both the rock temperature and the rock abundance, we can use the slope that we measure to derive those parameters. An important fact is that in all physical situations where if you're measuring the surface temperature with both channels or 4 channels or whatever it is, the shorter wavelengths will always measure a higher brightness temperature than the longer wavelengths. That's not the case if you're sensing different depths of the different channels, which turns out to be the case for our longest wavelength, but it's a subtlety. So the slope always goes this direction in this type of measurement. Here's how this looks. So basically we have, using these we actually use 3 different wavelengths for this case. We measure the brightness temperatures and then derive the rock concentration and the regolith temperature. So we fix the rock temperature, and then our 2 free parameters are this rock concentration in terms of a fractional area within the field of view, and the regolith temperature. That's kind of the background temperature, the blue stuff here. So this is what the maps look like. Again, we've filled this map in a lot since I made this plot, but so here's rock abundance. You can see the scale bar here goes from 0 to 3%. This is by area. So the base result that we find is that the moon's surface is extremely depleted in rocks. So here's showing basically the same scale. So all the blues are areas where there's essentially no rocks. It's less than 1% rocks by area. But you can see there's a lot going on here. So this big patchy region here is the near side Marius. That's what, when you look up at the moon at night and see the dark features, those are basaltic lava plains. And within those areas, you see lots and lots of rocks, and that's because the regolith is thinner there, and so impacts that occur in the maria tend to excavate more blocky material than in the highlands, which is out here. It's a much older surface. The regolith has had more time to develop. It's thicker, so impacts that hit in the highlands material tend not to excavate as much rocky debris. And you can see some craters in particular really stand out as being especially rocky, and it turns out those are the youngest craters. They tend to be as young or younger than this crater called Copernicus, which is an important age marker on the moon. So this shows this kind of age progression again, and actually the next talk, which is contributed by Rebecca Gent, is going to talk about this process in detail, but this is a very important observation, which is that over time the rocks on the lunar surface pulverized by impacts, and so the rocks tend to disappear as the regolith forms. We can actually quantify the rate at which these ejecta blocks break down on the surface over time, just by looking at the relative age dating of the different impacts. Okay, so that's rock abundance. So in the daytime, aside from very close to local noon, we see a wide scatter around this model curve. You'll also notice that the data points are a little below the model curve, and that's an effect that I'm not going to talk about, but it's important, and I think it's important for other thermal studies as well, which is that the albedo on a rough surface is a function of solar incidence angle. And I'll show you the formula that we use that actually fixes this and matches the data really well. And I would suggest talking to me afterwards if you have more questions about that. But the scatter around the curve here is due primarily to surface roughness. So in other words, when you have an airless body where temperatures can't equilibrate one another, basically you can maintain thermal gradients on extremely short length scales. And so even at the small scales where you have lots and lots of surface roughness, you can have a thermal gradient of hundreds of degrees between facets that are just a few millimeters apart. And so really no matter what your spatial resolution is, even with these 100-meter resolution pixels on the surface, we get tons of non-uniformity in the temperature distribution on the surface that creates a non-black body thermal emission. You cannot fit a black body to these data points, and that's shown here. So we did some models. This is an example 2D model where you can shine the sun on sort of a sinusoidal rough surface in this case at different length scales. So here's 0.5 meter down to 0.5 millimeter. So at 0.5 meter, the cold surface, the shadowed surface, is effectively thermally isolated from the warm surface, and so that's what produces that scatter in the brightness temperature data. As you go to shorter and shorter wavelengths, the surfaces can more efficiently conduct heat to one another. And by the time you get to about 0.5 millimeter, this temperature difference has become much more subdued. But it's still 50 Kelvin. Yeah? So even at 0.5 millimeter on the lunar surface, because it's so insulating, you can maintain this huge temperature gradient over distances of less than a millimeter. And that's just amazing to me. So what's shown here then is we did some special observations where we don't roll the spacecraft. Diviner has independent actuators, which is really nice because we can point anywhere on the lunar surface we want, independent of the spacecraft. So what we did is we kind of rolled and looked at the same spot on the lunar surface as the spacecraft flew over to get multiple different emission angles, which is this number here, and measured the brightness temperature in different wavelength channels as a function of that emission angle. And so this is an important constraint. If you're looking at this at a surface that has constant illumination, what's the roll-off of thermal emission as a function of that angle, basically. So the technique for deriving surface roughness relies on having multiple spectral channels. And this is what this looks like. So for a relatively smooth surface, I mean, this is still rough, but this is sort of a cartoon. In two different wavelength channels here, your brightness temperature spectrum is relatively flat, so you get roughly the same brightness temperature. If you increase the roughness, kind of catastrophically in this case, you get very different brightness temperatures. So in the short wavelength channels, again, you're preferentially measuring thermal emission from the hottest facets here. In the long wavelength channels, preferentially measuring the thermal emission from the shorter wavelength channels. So we can use this difference in brightness temperature to derive the surface roughness. So here's an example at the Apollo 11 landing site. So we targeted the site many times at different solar incidence angles. So this is looking at again, the brightness temperature difference between two different spectral channels. At local noon, it's essentially 0. There's a little bit of an offset for the emissivity, so that's into composition. Again, we can use that. But correcting it to 0, you get these curves, or these points that match up nicely with model curves, which are the black lines, for a surface roughness of roughly 20 to 30 degrees in this case. So that's a measure of the root mean squared slope, which is the peak in the histogram of the slope distribution. So we assume a Gaussian or normally distributed set of slopes. And we basically calculate all the temperatures on every single different slope and then sum them together using that probability distribution. And that's what these model curves are. So this number is huge. So 20 to 30 degrees, that's the typical, that's the most common slope, which is, when you think about it, that's very, very steep. I mean, you wouldn't drive a truck down that slope, right, on an incline. And the reason it's so high is because the thermal measurement is sensitive to every scale down to the smallest scale where a thermal gradient can be maintained. That's less than a millimeter. And so what's happening basically is that this surface roughness on the length scale of millimeters, which is very extreme on any airless body, is dominating this signal. And so it's just something to keep in mind that I think I'm pretty confident that any airless body that's subject to, well, that doesn't have an atmosphere to smooth things out or any kind of erosional processes that act like a diffusive process, it's going to produce little facets on these kind of length scales. So I would expect that asteroids should have a similar distribution. And we can actually map the surface roughness. We fit each point. We've expanded this map since this, but haven't got around to publishing it yet. So anyway, we can map surface roughness. Okay, so then if we throw out the rocks, these points up here, and concentrate on just the points that are more typical of regolith, we can kind of get at the regolith structure. So this is from a paper we published in 2012, doing model fits explicitly to the nighttime temperatures. And what we found was that because the data are so good, basically, the scatter in these data is very close to the measurement uncertainty, which is less than 1 degree. The models that had been developed up to this point fit pretty well, but not perfectly. So two cases are shown here. One is the dotted line, which is kind of the canonical. Actually, I'm sorry. The dotted line is a single layer uniform model, and you can see that it misses high early in the night and misses low late in the night. If you then go to the canonical Steve Keim model, which is a 2-layer model, including a fluffy layer on top and then a more consolidated layer below it, you get this solid curve here. It's a little bit hard to see probably in the back, but it does pretty well early in the night, but it misses high late in the night. And again, the errors here with that model are very, very small, and it's only because we have this quality of data that we can really see the difference. But what we found is we had to use not just a 2-layer model, but a gradational model. So starting with a density and conductivity at the surface and then increasing exponentially with depth. And if you do that, you can't even really see the model curve because it's on top of the data points there. But these are the residuals here, and they're within a couple of degrees. So we can actually map variations on the lunar surface in this thermal. It's essentially thermal. It's a thermal inertia or thermal diffusivity, basically. And this is the formula that we use for the density as a function of depth. And the parameter that we allow to vary over the lunar surface is this H parameter, which is essentially the scale height or the E-folding depth of the density and conductivity. We assume that the conductivity is proportional to density. I can get into that more afterwards if you want. And we allow this H parameter to vary, which is shown. So a set of curves here for different H values are shown, and the red data points are one point on the lunar surface that we've fit with, in this case, an H parameter of 6 centimeters. And this is what those profiles look like. So again, mapping this around craters, we see that the regolith is more consolidated, or at least more full of small rocks around fresh impact craters. And then over time, as the craters degrade and regolith builds up around them, the regolith gets more and more fluffy. So this is kind of the time progression. You start off with this profile, and over time it kind of diffuses down to this fluffier profile. This is density. And you can actually plot that in this way. So in this case, I'm plotting that 8 parameter value. Again, it's the E-folding depth of the thermal inertia, essentially, as a function of crater age for these points. So these are craters that have pretty good constraints on their ages based on smaller crater counts. So you see this trend from the youngest craters having the shallowest regolith to the older craters having deeper regolith. And if you fit a line to that, that turns out to correspond really well with the regolith overturn timescale that's been modeled since the 70s. So we're getting good agreement with regolith overturn models. The exact rate of ejecta breakdown turns out to be a little bit different from what the models had predicted, and that's the topic of the next talk. So I'm going to skip this, and you can feel free to ask me afterwards if you want to know exactly what model we use, but this is a summary. Here's the albedo function I was talking about. So this is based on work by Steve Keim in the late 70s, early 80s, but we've modified it to include these constraints from the diviner data. And here's a summary of the different constraints that we're using. So we've got the cool about the moon is that we've actually been there, and so we have depth profiles of the regolith properties and the heat flow and the temperatures at depth and all these great constraints that you can use to make sure that your thermal model is working properly. And here's a summary of the parameters that we're using up to this point. And again, just feel free to bug me if you want them. Okay, I don't think I have time to really do this, but we also have observations of lunar eclipse cooling. And this is, again, important because that eclipse thermal wave only penetrates to a centimeter or so. You get a good constraint on that upper layer. And again, it's comparable to, if you have an asteroid that's rotating with a period of a few hours, that's comparable to the temperature wave that we're measuring here. And so this really provides a good boundary condition on our model that we can't really get with the lunar diurnal data, because that's sensing what's going on in upper tens of centimeters. It doesn't really isolate that upper surface. The other cool thing about that is that if you think, again, back to this overturn time scale, the overturn depth as a function of time, the lunar diurnal cycle kind of isolates this region here from in terms of time, a few million years up to a billion years, whereas the eclipse cooling, because it's isolating this upper layer, isolates processes that are operating within that layer, which tend to occur on time scales of less than a million years, basically. And so in terms of the lunar geology, we can sort of isolate these different time scales of processes. So during the most recent eclipse, we've targeted with Diviner about 12 different eclipses now. So we've got this awesome data set. They're all available publicly if you want to look at the data. And we've also done some observing with a ground-based telescope in Hawaii, using thermal imaging at comparable spatial resolution to diviner, but with much better spatial coverage during the eclipse because we can scan around to different parts of the lunar near side during the eclipse. So we targeted a few different interesting features. Maybe I'll just mention one in the interest of time. So these what we're calling cold spots were discovered by diviner and never would have been known except for the thermal data. So around some impact craters, not all of them, there's this huge, extensive region of fluffy materials. You see them as anomalously cold regions at night. It means that they've got a lower thermal inertia, and they clearly are associated with the impact. And the problem with them is if you then look at how thick that fluffy deposit must be in order to explain the thermal signature, it's got to be comparable or larger than the diurnal thermal skin depth, which is at least a few centimeters, depending on the thermophysical properties. So you take that thickness of the deposit that it would have to be to maintain that cold temperature throughout the winter night, multiply by the area, you get a volume, try to put that volume back in the impact crater that seems to have produced it, and it doesn't fit, like 2 orders of magnitude. So there's something else going on during the impact process that's disturbing the regolith around these impacts and fluffing them up. So it's decompressing the regolith and producing this fluffy deposit. And as of now, don't have a really good explanation for how it occurs. So it's an open topic. We wanted to target these features during the lunar eclipse to see if that upper layer, the upper centimeter, is also different from the surroundings, in addition to that tens of centimeter layer. So here's an example of one of these. So here's the impact crater. It's warm because it's got lots of large and small rocks, and then around it is this cold spot. Let's skip all this stuff. Here's a movie. This is not a cold spot. This is a crater. So this is from the ground-based data looking at this is Campbell crater during eclipse. So the main thing you notice are rocky the rocky walls of the crater, and there's some around the central peak. So the rocks are warm in the eclipse. So they've got a higher thermal inertia. This is a lunar swirl. These are enigmatic features on the lunar surface that seem to be produced by localized magnetic fields. They're not really well understood. And we wanted to see if it was still apparent during the eclipse. You can see we lost track of it there and then tried to find it again. It turns out it did disappear during the eclipse, which means that the swirls don't have any anomalous thermophysical properties in the upper centimeter, which was an important constraint on formation. Overall, we find this upper centimeter layer on the moon to have a thermal inertia equivalent to about 10 MKS units, which is about a factor of 5 smaller than the underlying 10 centimeters. And again, we have to use an exponentially increasing thermal inertia to fit the data. So this upper centimeter typically has a much lower thermal inertia than the deeper layers. So again, the time scale of the thermal wave is very important, because if you're only measuring this upper centimeter, you're going to get a very different number for the thermal inertia of the body than you would if you can sense down to depths of 10 centimeters. Okay, here's a cold spot. Turns out it doesn't show up at all during the eclipse. In fact, the only thing you see during the eclipse is the warm central crater. The cold spot itself, which should be out here, is no different from the background, which is very strange. In fact, it turns out that the temperatures are a little bit elevated within the region that should be cold, which is here. And so what this means is that somehow during the impact process, if this is the pre-impact regolith, you've got the fluffy layer on top that's a centimeter on top of this more consolidated regolith here. During the impact, somehow this fluffy material gets swept off, maybe by an expanding vapor cloud or ballistic secondary particles here. And then at the same time that you sweep off that surface fluffy layer, it decompresses this underlying layer. So what we measure is the very surface is actually more fluffy and, less fluffy than previously, but the underlying 30 centimeters are more fluffy. This is just kind of a cartoon of what we think is going on. We don't really understand these features. Okay, so I'm going to conclude this talk by saying that, so I I've kind of just tried to highlight some of the high-level features of this data set, but I hope you agree that it's very rich and diverse, and I didn't even have a chance to talk some of the other aspects, including the composition and volatiles. But we've got a kind of unprecedented view on the thermal behavior and the thermophysical properties of an airless body here that I think has applications beyond just the moon. And so I hope we can start a dialogue comparing the moon to some of these other observations that we have of small bodies, which I think will kind of yield insights both directions, not just, this diviner data set informing the small bodies data sets, but I think also vice versa, because there's a lot of aspects of the diviner data that we still don't understand. And so I think this could be an interesting conversation to have. As I said before, diviner is still acquiring data as we speak, and so this data set, which is publicly available on the NASA Planetary Data System, is free for you to use. So I encourage anyone who's interested to pursue that. Thank you very much.
Okay, so it was an exciting tour through what we can learn from disk resolved data. Are there any questions or comments?
So you showed the calculation that showed that the contrast of the surface facets with temperature depends on the scale, and then you had a model for roughness. So I was wondering what in the model, what did you use? Did you basically assume that all the facets were independent of each other, meaning that basically you're modeling big scales, or is there some assumption about smaller scales?
That's a good question. So for this model, we assumed that the facets were independent from one another, but we did include a ground heating effect where you basically eliminate part of the sky for a facet that's sloped, so it can see a warm surface out here during the daytime. So we include that effect, but we don't include the contribution of other facets. But we do include a statistical shadowing model. So basically at each point along these curves, there's some fraction of the surface that's in hard shadow based on, there's a really nice, elegant model by Smith from 1967 that calculates that fraction as a function of solar incidence angle. We have to looked at using, I showed that nice 3D model in the beginning of the talk. You can use that model to put in any arbitrary roughness, including surface-to-surface radiation, and we've also done that. It changes the result a little bit, but not hugely.
Other questions?
This is fascinating, and of course the moon has its own scientific interest, but I'm looking at it as an asteroid man, as excellent ground truth. And so one question I was going to ask is, you derive the thermal inertia from the night side temperatures, and that's a natural thing to do if you can. We can't. We only see the day side normally unless we fly somewhere. Have you tried to measure the thermal inertia from the day side temperatures? Have you tried to see if that matches what you get from the night side?
Yeah, the answer is no. But if you looked closely at the eclipse data that I showed, after the eclipse, when the sun was back out, you could see lots of little little spots, and those are rocks. And so what that's telling me is that at least for the rocks, the thermal inertia is high enough or different enough from the background that they would have a different daytime temperature, at least maybe early in the morning. So in principle, it's possible. We don't have to, so we don't, because it's a lot easier to do at night. But that would be an interesting thing to look at, to see if we could also do it using instead of using this difference, use this difference. I mean, you can see why we use the time data just by looking at this plot, right?
Yeah. In fact, your model has all these bells and whistles to it that we usually cannot afford to apply on our data sets. So it'd be very useful to see what you get from the day side temperatures, and also for different levels of model sophistication. to tell just how much of a difference that makes in fitted thermal inertia. That would be extremely useful. I would quote that paper over and
Yeah, I
over.
mean, one good
I
proposal.
bet I'm not the only one in this room.
Yeah, I mean, I think an interesting proposal that I would review highly would be to take the diviner data and pretend that the moon is an asteroid far away, and see, what would you measure? And I think the data are there to do that.
So related to that, how easy are the PS diviner data to access and use? If Migo wanted to go in and grab daytime data himself and model them, is there a lot of, a lot of times with PDS spacecraft data, if you don't know the instrument, you can't really use the data very easily. Is that true with diviner? Or?
We've tried to make it as easy as possible with, just based on similar experiences to what you've had. And, I mean, I've dealt with frustrations over other people's data sets as well. And so the best thing to do is to go first look at what we're calling the gridded data products, and these things that are binned. It's a binned in terms of different parameters, including local time or mapping cycle, depending on what you want. You can find, for example, if you just want the temperature at a particular local time on the surface at a particular location, the gridded data products are pretty easy to use. But if you want to get into the nitty gritty of the data, they're all there as well. You can actually get back to the fundamental measurement if you. But the best thing to do is to look at the gridded data first. If you have any problems, just email myself or Dave Page, the PI, and we're happy to help.
Really quick.
Yes. Well, I hope it's quick. So I'm not fully understood how you derive the rock abundance, as I told you yesterday, and still quite. So here, to draw those curves, you have to know the thermal properties of the regolith in the rocks, right? So you have an assumption behind it. So the regolith has this thermal inertia and all these thermal properties to draw those lines. Oh, and the rocks, you gotta know them, right? And then the parameter you fit is the rock abundance, so the abundance of one against the other components. Is that right?
So depending on how many free parameters you choose to fit, it can be an overdetermined system or under, depending. So basically, in this particular case for this 2011 paper, what we did is we only used 3 of diviner's channels, which have the best sensitivity to nighttime temperatures. Those are the 3 vertical bars shown here. So with those 3 parameters, we could only vary at most, those 3 constraints, we could only vary at most 3 parameters. We chose to vary 2, and the 2 that we varied were the rock concentration on the surface and the regolith temperature. So we assume there's only 2 components on the surface, the rocks and the regolith. And in this case, we assumed a rock thermophysical model. So we had the thermal inertia of the rocks, but we didn't make any assumption about the regolith physical properties. And so what's derived then is we can get the regolith thermophysical properties from the measurement and the rock abundance. I have a postdoc now who's working on improving this, and she's using more spectral channels to make no assumption about the rock thermophysical properties, and then pull out the rock properties as well as the regolith properties. Yeah. One of the questions that always comes up that no one's asked yet is, so I guess not always, is what do you mean by a rock? How big of a block of material are we sensitive to? And the answer for the moon is about a meter, half a meter to a meter. Anything smaller than that, we can't see it, basically.
All right, great. Thanks, Paul.
Okay. I'm giving another talk, so we can.
So you've only got about 10 minutes for the next talk. So our next talk is by Becky Gent on moon's regolith properties from thermal IR data, and Becky has disguised herself very well as Paul Hain this morning.
Okay, so Becky sends her regards and apologies for not being here. And this is based on ongoing work, but also, if you're interested, I recommend looking at the geology paper that we published, the paper published in Geology several months ago in 2014. Okay, so the basic idea here is that the lunar regolith has developed over time. So the moon didn't start out with this layer of fluffy material on its surface, and still in places, especially around those fresh impact craters I mentioned in the previous talk, you still have boulders and smaller rocks on the surface. And over time, the bombardment of the lunar surface by impacts fragments and pulverizes these rocks and produces this fine-grained regolith on the surface. There may also be other processes that break down these rocks, including thermomechanical processes, which Marco has worked on. So the end result is that over time, you develop this fluffy regolith, and with the diviner data, we can actually constrain the rate at which that regolith forms. So in this talk, we're going to talk about the fate of ejecta blocks on the surface. So if an impact does penetrate down beneath the regolith and throws out blocks onto the surface, how long do they last before they're pulverized? And then we're going to look at some features that are very interesting features that surround some large impact craters that seem to cover up the background regolith. And then also these pyroclastic deposits, which are the end result of fire fountains, essentially, volcanic eruptions on the lunar surface. Okay, so the two different data sets we're going to look at in this talk are both the diviner data, which I've already described, and also radar data, primarily from Arecibo. So using Arecibo in the bistatic mode, where you transmit from Arecibo and receive at a different station. The Lunar Reconnaissance Orbiter also had a radar instrument on board that's called Mini-RF. So an example of the Mini-RF data is shown here. This is a swath over the same crater from the radar instrument on the left, and then this is diviner rock abundance here. Same thing on the right. So we're going to talk about the similarities and differences between these data sets in terms of the rocks on the surface and the rocks in the subsurface that we can sense from these two different data sets. So the thermal data that we're talking about from diviner, as I said before, is really only sensitive to the upper surface in terms of the temperature, but the upper tens of centimeters in terms of the thermophysical properties. The radar penetrates down to several meters, depending on the frequency of the radiation. So this is kind of a cross section of the anatomy of an impact crater. So again, you've got this regolith material on top. The uppermost surface is very unconsolidated and fine-grained, kind of a dust. And underneath that, you've got maybe several meters up to tens of meters of regolith that's more consolidated than this fluffy layer, but still particulate in nature. And then below that, you've got the lunar bedrock. So a large enough impact will penetrate down to the bedrock and excavate some of that material, which ends up as these blocky ejecta, which tend to pile up close to the crater rim, but also get thrown out to very large distances. So I went over diviner rock abundance. I'm not going to belabor that here. I also showed this plot from this Banfield paper. And again, over time, after those ejecta blocks get excavated from the subsurface and thrown out onto the surface, this is a crater that's maybe a few million years old, progressing to a crater that's a billion years old. And you can see that by the time you get to maybe a few 100 million years, all of those rocks that were thrown out onto the surface have been destroyed and pulverized by impacts. And so we can actually plot those rock abundance values as a function of the age of the crater. So here's the the age of these different craters based on the concentration of later impacts that occur on the ejecta surrounding the craters. And so you get this nice distribution from having lots of rocks on the surface for young craters to not many rocks for older craters. And we kind of lose leverage once there's not enough rocks to measure anymore out here at about 1 billion years. This technique is sort of valid from 1 billion year timescales and shorter. This is kind of the lower limit too. So we can't do much below several million years as well. So we found this relationship where we could actually, if you can measure the rock abundance, which we can, diviner, around a particular impact crater, you can actually date it based on the rock abundance using this relationship. And so this is kind of a new, interesting technique that where you can actually use the thermal data to measure or estimate the age of a particular impact crater. The other thing that this tells you then is because you've got an age as a function of time, and you've got the rock abundance as a function of time, this gives you an estimate. You've got the rock abundance as a function of age. That can give you an estimate of the rate at which the ejecta are being produced on the surface. In other words, starting from this rock abundance value, how long does it take to eliminate all those rocks and end up down here on this part of the curve? You can even look at the changes in the rock breakdown rate over time. So then, comparing the two different data sets, here we've got on the left, we've got the Arecibo, this is circular polarization ratios. This is basically a measure of the blockiness in the volume integrated column of regolith. So in the case of the radar data, you're looking at primarily subsurface rocks. So this would include things that the infrared data can't see, basically. On the right, you've got the diviner rock abundance. And so the first thing you notice is they don't match up. So in this case, the interior of this crater tends to be very rocky, whereas the distribution of subsurface rocks from the radar data is much more uniform over the interior and the ejecta region of the impact. And then in this case, for Copernicus, the rock abundance is actually pretty low at the surface, but you see this massive amount of rocks in the subsurface. And so by comparing these two different data sets, we can get a constraint on the changes in the rate of regolith accumulation and the way that the regolith protects subsurface rocks from being destroyed on the surface. So we've got this data set, again, that's publicly available for radar CPR data. And we can make these comparisons from many different craters that both exist in the radar data set and the diviner data set. Okay, so this is just emphasizing this point that, so here's a crater that is essentially one of the oldest craters on the lunar surface. It's over 3 billion years old. And in this case, diviner wouldn't see any rocks at the surface at all, but you see, again, lots of rocks in the subsurface. So the rocks in the subsurface seem to persist much longer than the surface rocks, which maybe is not surprising. We don't see any, so you could do the same thing, you could try to do the same thing that we did with the diviner rock abundance data with the CPR data from radar, but you don't see any correlation between the CPR data, the subsurface rockiness, and age. So here's the, this is crater age here, and this is the CPR value. There's no correlation there. So what that's telling us, basically, once this regolith develops on top of those rocks, they're protected from being destroyed by impacts. So the implications of this is that we can use diviner to estimate the age based on rock abundance, but we can't do the same thing with radar. And what that means is that most blocky ejecta for these, especially for these older craters, are in the subsurface. And I'll get to these radar dark halos in the next part. So what is she saying here? So mapping of small rocky craters with diviner and radar dark halos. that's the next part. So we'll save that for a second. So this difference in the erosion rate or the breakdown rate of rocks between the surface rocks and the subsurface rocks provides a constraint on the rate of change of the rock breakdown process. And the thing that we notice is that the breakdown rate of rocks much higher very early on when the rocks are exposed at the surface than later on. And one possible connection to make it is, could this be evidence of thermal cracking? Because the regolith, in addition to protecting those rocks from impacts, also protects those rocks from thermal oscillations. So the rocks that are exposed at the very surface experience much greater diurnal temperature cycles than those in the subsurface. So this, both the impact comminution and also the thermomechanical breakdown of rocks would be more extreme at the surface than for subsurface rocks buried by a centimeter of regolith. Okay, so I mentioned these radar dark halos. So around many of the larger craters on the moon, it's hard to see in this plot, but in addition to having lots of rocks in the subsurface very close to the crater, there's these huge regions, sometimes several crater diameters around the impact crater, where we see very few rocks. So there are these dark regions in CPR where we've got very few surface and subsurface rocks. So if you look at the diviner rock abundance down here, we also see the dark halos. That means that those regions have regolith with very few rocks, both at the surface and the subsurface within this ejecta region. So what you can do then is look at later impacts that occurred on top of those radar dark halos. And what you see is that below a certain size, the impacts that occur in the radar dark halos don't excavate rocks. And an example of that is shown here. So here's a 430 meter diameter impact crater. And there's lots of rocks that crater excavated, which means it penetrated through this regolith deposit to the bedrock below. And then here's one right next door, roughly the same age. We're just a little bit smaller at 330 meters, and it didn't excavate any rocks. So if you look at the crater depth to diameter ratio, which is being conservative, maybe 1:10, but more typically it's closer to 1:5, this tells you that the thickness of this radar dark halo deposit is roughly 10 meters, maybe 30 meters. So this signature of a rock depleted region around these impact craters is long-lived. So we see this even in 3 billion-year-old craters, as I mentioned before. So then what about the regolith thermal inertia? We might expect that this deposit of fine-grained material around the impact crater would also have a lower regolith thermal inertia. That's what this map is here. You can see there's not really a signature. So the radar dark halo would be this region here. You don't really see it much, but what you do see here is this stuff up here, and that's a pyroclastic deposit, which is the topic of the next part. So Aristarchus crater is sort of here by coincidence, but this feature up here is the Aristarchus plateau pyroclastic deposits. This is a volcanic deposit caused by the violent eruption of lava on the surface. So it throws out lots of, they tend to be sort of spheroidal beads of glass onto the surface, and a lot of these were collected by the astronauts during the Apollo missions. So what we see in the radar data is this deep pyroclastic deposit appears to have many fewer little rocks mixed in with it, which means it's probably pretty thick. And again, with diviner rock abundance data, we also see the signature of very few rocks on the surface in this pyroclastic deposits. And many of the impact craters that have occurred within this pyroclastic deposit don't excavate blocky material, again, which means it's pretty thick. I showed that already. So our conclusion so far for the pyroclastics, we don't really understand why the thermal inertia is lower, as I showed here, so this is regolith, essentially regolith thermal inertia. You can see the pyroclastic shows up as having lower temperatures means lower thermal inertia. It also has depressed rock abundance. Maybe that's due to the fact that the material that's forming the deposit is this erupted glass, and so basically it's just filling in the whole surface and being placed on top of the rocky material below. So there's also volumetric depletion in rocks. So this low thermal inertia nature of pyroclastics is not consistent from one pyroclastic deposit to another. So there seems to be a difference in the style of volcanic eruption on the moon from location to location. So that's one important constraint based on these thermal data. So one idea we have to explain the low thermal inertia is maybe if you had very uniform glass beads, which we know they are from these pyroclastic eruptions, those uniform glass beads would actually have more void space between them than if you had a size distribution of particles. If you have a size distribution of particles, then basically you can fill in voids between the particles with smaller particles. Whereas if you have uniform spherical beads, you can get very high porosities. So that's one possible explanation for low thermal inertia. And that's all she had. So thank you.
Any questions for Becky?
I tried to get her online, but I think it's like, what, 2 a.m. there or something right now. So 5 a.m.?
Oh, she totally could have done it.
Yeah, just get up early.
I have maybe a crazy question, but could it be that you have some material from the impactor that mixes with the pyroclastic?
You mean this impact?
Yeah. Like if you have a carbonaceous chondrite impactor, maybe that could lower. I understand it's difficult to preserve material from the impactor because the high speed is probably like several tens of kilometers per second, but
yeah. So typically the ratio of, I mean, the amount of material that is emplaced in the ejecta around impacts is largely the target material, not the impactor, right? So, and I don't remember the exact ratio, but it's more than 100. You know, so you've got many times more material being thrown out onto the surface from the target material than from the impactor itself. So my intuition is that I don't think mixing a small amount of an unusual impactor material could affect that. But one area where the composition of the impactors matters is in potentially the space weathering of the lunar surface, and so basically you mix in all the materials that impact the lunar surface over billions of years. So there is some contribution to the composition of the lunar regolith from the micrometeorites that impact.
Okay, thanks. We'll have to move on to the next talk. And our next talk, and the last one before the coffee break, is the effect of slope distribution on surface temperature of airless planetary bodies by Lior Rubinenko.
So, hi everybody. My name is Lior, as I said, and I'm here to present my master's thesis, which is done in collaboration with of course, my advisor, Odell Aronson, and also Paul Hain, here, and then Robert Shogopper from University of Hawaii. And I'm here to discuss the role of the surface roughness when trying to model temperatures or measure actual temperatures on airless planetary bodies. So, So the motivation for actually my entire thesis, I guess, is the lunar cold traps, which Paul has already mentioned, and I'd like to talk a bit more about them. There's this, you can say, maybe I should in the 20s. In the 20s, a very famous physicist called Urey, which discovered a small thing as the deuterium. Actually, he speculated that there are places in the solar system, that might be permanently shadowed. And he assumed that those permanently shadowed places would be very good places for volatiles to be trapped in. And why is that? That's because of course, the very low temperature that they can reach. So this border temperature, this temperature limit varies, I guess, depending on who you speak to, but it's between 110 and 120 Kelvin. And that, of course, relates to the evaporation rate in vacuum, which is correlated with the vapor pressure of the volatile water in that case, and its temperature. So the temperature we seek is below 120 Kelvin or 110 Kelvin. So in order to find those cold traps, one can either send this arrow and just look for them, look for shadows and look for temperatures, and one can use less advanced method, you can say. So Smith in 1967, which Paul has already mentioned, wanted to check what's the if you have a rough surface, what's the portion of the surface which will be shadowed, and we did this strictly out of statistical considerations. If given the root mean square slope of the surface, you will get what's the portion of the surface which is shadowed, which is actually illuminated. This is called the shadow function. And Benfield et al., which Paul is a co-author were able to model go the other way around, model the roughness of the surface using the temperatures, and Paul already talked about it, and I won't be talking about it. But as you can see, during sunrise and sunset, the model doesn't match the actual root means the actual statistical properties of the roughness of the surface, and that's due to reasons I'll explain in a minute. So this is exactly what we need to account for, right? Because when trying to find those cold traps, only counting the shadows, only finding the amount of shadow a surface would have is not really enough, right? We have to account for, of course, reflection and emission, which play a very important role in the shadowed part of the rough surface. And I think the first attempt to tackle this problem was made by Ingersoll in 1992. Ingersoll assumed there's a spherical crater with a certain depth to diameter, 1 to 5 actually, and was able to plot the ray path in this spherical crater out of optical geometry considerations. Very, very, very simple, and very get the relation between the equilibrium temperature and the geometry of the crater and the surface properties, the albedo, the emissivity of the surface, and this is the diameter to depth here. So given the incidence angle, the elevation angle on the surface, you could exactly on the crater, sorry, you could exactly know the equilibrium temperature. So okay, the problem with the Ingersoll solution is that, well, it's only good for spherical craters, and what we're trying to do is to come up with a 3D numerical animation model and combine an efficient heat diffusion algorithm. And I know I can use profanities here, so I'll use Crank-Nicholson. That's the method we use to solve the equation. And eventually, our scientific goals are to link the temperature distribution to the slope distribution, to the roughness of the surface to its statistical slope distribution, and investigate various types of cold traps. And I'm going to discuss which types of cold traps in a minute. So, okay, I don't think I really need to explain this. We've heard this quite a lot the last couple of days. Thermal conduction, the surface gets heated during the day, and then the subsurface reheats the surface during the night, and this is done by solving this equation. A little bit more complicated to actually see which, to account for which facet on the surface actually sees the sun and what extent, how much solar flux reaches every part of the surface. And this is done by accounting for the angle. The normal is missing here, so imagine there's a normal here. By accounting for the angle, the cosine of the angle between the surface normal and the angle to the sun. And of course, the surface to surface, which is to consider thermal radiation and reflection. And this is done by accounting for what's called the view factor. And the view factor is actually a measure of the angular size every facet has from the point of view of every other facet. Okay, so this is unitless. This is only an angular size. So in order to solve this, we used actually a method that was used in computer games in the 90s. I don't know this game. It's called Castle Wolfenstein. And this method is called ray casting. And it's a very simple method, very similar to ray tracing, which you already know. But in that method, the character who stands here shoots rays to every direction in the room until one of those rays hits wall, and then it draws the wall. The engine draws the wall at that position. Very simple, I guess. So we do the same on the moon. Let's say I want to see if that facet sees that facet or not. So first I shoot a vector from that facet to that facet, and then I draw the topography on the same plane. I draw the topography to the other facet. Now, it's enough. First, it's enough to see that if those, if the blue curve, the purple curve is somewhere above the yellow curve, which is very efficient numerically to check, it's a very easy test. And this facet cannot see this facet. So, okay, this is the model. So it's a very general model. And I'm going to show you some of the results. So first, to show you that I'm not talking nonsense, I want to show you the model shadows of actual lunar topography. And this is topography that was obtained by LOLA. LOLA is an instrument that sits on the LRO, the same orbiter that carries the diviner Paul was mentioning earlier. And we modeled the shadows on this area for this elevation angle, which is 10 degrees. This area is about, this entire thing is about 60 kilometers, 2 degrees on the equator. And the same area was actually pictured by, photographed by another instrument on the LRO, which is called the LROC, the LRO camera. Not surprising. So, and this is the actual image. I hope it's bright enough. But as you can see, the shadows match pretty well, I guess, with the topography. So we can actually simulate the shadows pretty well. There are some artifacts of the LOLA interpolation. LOLA records the data vertically, so we have to interpolate in between those vertical lines, and so we get those ears right. And some craters are missing, but overall, I think it's a good fit. Another test we did was check the Smith model I told you about earlier. So Smith, given an RMS slope and an incidence angle, can tell you what the portion of the surface which is shadowed. So we did the same, and get again pretty good fit. Smith, nevertheless, doesn't account for what's called double shadows. This is a bit complicated, I guess. So we all know what self-shadowing is, I guess. It's when sun has set for a certain facet, because it's not true for the entire surface, right? The sun sets at a different time for every facet, so that's self-shadowing. Single shadowing is when, I don't know, a mountain somewhere or a hill somewhere casts a shadow over some facet. And double shadowing is when another mountain out in the back, let's say a larger mountain, casts a shadow on both the hill and the facet. So Ingersoll counts Smith counts that as two shadowing, right? Because this facet has twice the probability to be shadowed. which is actually shadowed only, counted as only once. The shadowing counted only once. So that's why our model is a bit more illuminated in very high hardware. And talking about the Ingersoll solution, so Ingersoll predicts if this is the spherical crater, so he predicts energy will be distributed evenly along the crater's walls, and that what gives the crater, the shadowed part of the crater, a uniform temperature. So it doesn't matter. It doesn't matter where the spherical crater is actually. After enough time, after enough reflections and emissions, if it hit all the walls, the shadowed part of the crater will have a uniform temperature. And as you can see here, this is the crater we modeled using a model, and this is the energy distribution along the shadowed part of the crater. And as you can see, it's uniform, both IR, visual and visual reflection, I mean, and IR reflection, which I don't think we need to account, so we usually neglect it. And this is pretty cool, I guess. This is a simulation of 24 degrees. Paul showed you, I think, a high resolution simulation. This is a, I guess, lower simulation resolution. So this is the same topography I showed you earlier. Now the temperatures, the day temperatures is during the night. So the sun rises on this part of the surface, and then sets on this part and travels along this line, because it's near the equator and the obliquity is near 0. And if we match those temperatures with the diviner, this is the diviner temperatures, the diviner collected temperatures. If we match those temperatures with the diviner collected temperatures, and I'm going to draw a cross section through the topography here, you can see that our temperatures, I can predict the temperatures pretty well, I guess, for a given incidence angle and a given topography. So the blue one, the model, and I should say that. The blue one is the model, and the red one are the diviner measurements. So following my ancestors, I guess, we decided to build pyramids on the moon. So this is a polar-facing pyramid. This side faces the pole, and the angle here from the aspect is different by 5 degrees from the pole. So this is tilted 5 degrees from the pole. And we tried to see if, briefly illuminated areas could serve as cold traps. It was very interesting, behind the positive reliefs, I mean. Here, as you can see, the temperatures are not low enough to serve as cold trap. And I'm going to explain exactly why. So 1 degree is one too many. That's how I like to call it. And why is that? Because at 1 degree, you're already at 21 watts per meter square flux. And that's too much to serve as a cold trap. If you remember, I told you that the limit, the maximum limit is 120 Kelvin, and 140 is already too much. To get 120 Kelvin, you need a ½ degree a maximum elevation angle, which is not possible on the moon due to obliquity. But then we remembered that the sun in the pole, or close to the pole actually, for co-latitude 80, for example, rises very, very slowly. And when I say slowly, I mean it covers very big azimuth compared to the incidence angle it covers at the same time. So for a ½ degree incidence angle, the sun will cover an azimuth of almost 3 degrees. So if, for example, there was a positive relief tilted 2.7 degrees towards the pole, and the sun would just go behind this positive relief before it got to 0.48 seconds, we might find cold traps actually, and we are still looking into it. So I'll skip, I guess, because it's time. And now I want to talk about the role surface roughness has on the temperature. And okay, it doesn't work, but you have to believe me, this video used to work. So this is a random surface, which means this is a Gaussian process, a Gaussian random field, where every facet here is a different Gaussian random process. fitted with some kind of a power spectrum. And what I drew here is I drew the Ingersoll solution. I remember I told about the Ingersoll spherical craters, and the equilibrium temperature a spherical crater would have for any solar zenith angle, for any latitude, actually, the equilibrium temperature. And for two types of crater, this is a 1 to 5 to diameter, and this is 1 to 10 depth to diameter, which are very common on the moon. And those temperatures are the shadow temperatures of rough surfaces at the same those zenith angles. And as you can see, and it was pretty surprising actually to me, rough surfaces could serve as better core traps than craters. Okay, and that's weird, right? Because we think craters are, well, they have shadows, so they must be colder than all other surfaces. But that's not entirely true. And why is that? In the surface, we get this lens effect, right? The fact that even when a small portion of the surface is illuminated, the entire crater gets energy, the energy distributed along the shadowed part of the crater, and the shadow is actually pretty warm. Actually, too warm to serve a core trap below 80, I think 80, 85 for 0.2, for 1 to 5 depth to diameter. And this effect even increases when I'm increasing the root mean square slope to 25 degrees. It was 5 degrees before, I didn't say, now it's 25 degrees. So core traps actually appear very, very low, at very low incidence angles. And that's because every facet sees much more sky than other facets, right? It sees less other emitting facets and more sky, so it's generally colder than the crater that reflects the energy so well. Okay, so let's talk about conclusions. So now we have actually just finished it a couple of weeks ago. We developed a 3D numerical illumination model that is applicable for any general topography, and compared it to successfully to several models that in the past. And I want to talk about briefly illuminated core traps. So while they might exist, as I told you, they are very small and I would say rare and negligible in area for the moon. So we might find them, but I don't have much hope for that, especially with the lunar obliquity that usually ruins everything. And what we can do to improve past models, and this is, I think, very, very important, is that the equilibrium temperature during sunset and sunrise is very different from the actual surface temperature. And past models, such as the Benfield model I discussed earlier, and don't take this into account. So we have a better chance to actually simulate the temperatures during dusk and dawn, and for surfaces that don't have a Gaussian distribution, which that was the assumption in past models. And that is really important, right? Because not all surfaces have a Gaussian distribution. I guess most surfaces don't have Gaussian distribution. Another thing I would like to say that slope distribution has a profound effect on core traps. As rougher the topography, random topography, I mean, you'll have less sky visibility, but some facets might be still cold enough to hold volatiles in condensed state, to have low enough temperatures to be core traps in very low latitudes. So you get a very high temperature range, but warmer shadows. Sorry, colder shadows than spherical craters. And maybe most important thing to say here is that we don't know how the moon looks like the different scales, right? If it's made out of many impact craters, many small impact craters, or rough topography, and that is to be found in the future, I guess. Thank you.
Okay, questions, comments?
So I'm just curious about how you go about calculating the temperature for a particular facet, because basically if you say that the temperature depends upon not only the direct solar illumination, but the contributions from other facets. So, okay, I can go and look around and I can find all the other facets, but the temperature of the other facets depends on the temperature of the facet that I'm using. So how do you proceed with that? You do something iterative, or how does that work?
It is an iterative method, yeah. So you go time step after time step, and then sum the contribution of all other facets for the particular time step you're interested in. Then you get the solar, the total flux, I would say, not only the solar, the total flux for that particular time step, and then go on and calculate the temperature with conduction, account for the conduction temperature.
Yes, and you can solve it for spherical shapes by integral equation. I see here the very important reference of Boole, 1968, who was the first one, I think, who solved this problem without heat conduction, but for spherical data with all this self-heating and so on. And this is the mass of all these papers, I think, also set of Ingelson. But now I learned to also apply a lot of other shapes. Do you know this very new paper by Davidson et al. 2015? In this paper, I think it just came out different surface models, roughness models like spheres, like fractal models, and many other ones are compared. And maybe it's a good addition to your work here.
Okay,
do you know that? No.
No, I don't know it. And
I can give it to you. It's new.
Thank you very much. Yes.
Yes. Boole was one of the people that I acknowledged in the beginning of my talk because the Ingersoll solution is based on his work, and I recommend looking at his PhD dissertation. Has not just the spherical bowl-shaped craters, but many other geometries too that you can use as a test for your numerical model. Not all of them have exact solutions, but he makes some really interesting approximations that are still good tests. But I guess my question for you or for the group is, I know that a lot of the shape models, or a lot of the thermal models for small bodies they start with a shape model and then imprint some kind of roughness model on top of that. In my understanding, it's typically a bowl-shaped crater model. Sounds like bullshit crater when I say that. Basically, you put many different craters on top of that surface with some concentration, and I guess that would correspond to an RMS slope. It's not a Gaussian. I don't think it's a Gaussian distribution. It shouldn't be. It should be like bimodal or something.
Well, it's not a Gaussian distribution, right? Yeah.
Anyway, I guess the question is, what are the differences in the predicted thermal emission for the Gaussian random distribution of slopes versus the bowl-shaped crater distribution? And would that be detectable? And if not, what are the implications for the actual surface temperatures on the body?
So for a single crater, a single crater has a warmer shape than your typical random topography, I guess. So I would expect maybe many spherical craters, or bowl-shaped craters, to have each one of them would have its own very warm shadow. So I have to say we didn't check yet, so I cannot give you the full answer about that. But we should look into it. Yeah.
So I think the Rositas and Green paper looked at that from 2013, right? So there's a study of at least the random Gaussian surfaces with bowl-shaped craters, and then the Davidson paper that was just mentioned also looks at random Gaussian surfaces, fractal surfaces, sort of parabolic trenches that are used for comets sometimes, and spherical. So there are they look at that with different emission angles and everything. So you can read up on some of those differences. I think so. I have a question. So for we have some small body missions coming up too. We'll get good spatially resolved data. How hard or easy would it be for you to apply your model to an asteroid? If you have a shape model for an asteroid and sort of seeing how low in latitude volatiles might might
I guess
be
pretty easy. I guess. Yeah.
that'd be an interesting thing to say.
I like it.
Any other questions or comments? Let's thank our speakers for. Thank you. And if our bosses don't have any announcements, I think we can go to our coffee break. Coffee break.